Okay, so let's discuss some examples of regular expressions. So this expression 0 or 1, 0 plus 1 star, so this is either the letter 0 or the 0, 1 and letter 1. Apply the cleaning star. This is all binary strings, right? Including, of course, the empty string. Okay, so this is all binary string concatenated with 0, 0, 1, concatenated with all binary string, which means all binary strings that contain 0, 0, 1 in them. Next. Okay, so 0 star is all all strings are made out of zeros. The more interesting expression is the expression in the parentheses. So let's replace 0 star by epsilon inside the parentheses. So then we get 1, 1, 1 star, right? So this is just all strings that are made out of ones, where the number of ones is a multiple of 3. And now, if you think about it like that, then the 0 stars are just paddings, right? So this expression generates all binary strings where the number of 1 is a multiple of 3. Okay. Empty set concatenated with 0. Well, empty set is just a set, the set that have no element concatenated with the character 0. Well, we can think about this as, the string containing the string 0. And the concatenation here is an empty set because the left side has no string to concatenate with. As such, the string you can generate no string with this expression, which means it's the empty set. Okay, so let's look here on the middle. 0, 1 star is, of course, all the string where we have 0, 1, 0, 1, and so on. And then this first parenthesis says that we can prefix it with 1. And the later one says that we can suffix it with 0 if we want, right? So really what we get here is all binary string that are made out of 0, 1 alternating. Right. Okay. Next one. So here, let's think about it, right? So we can start either with an empty string or a 0. Okay, so let's ignore it for a second. The second parenthesis says 1 or 1, 0, right? Star, right? So clearly we can generate an arbitrarily long string of 1s, right? But what we cannot have, right, is 2 consecutive string of zeros, right? And if you think about it a bit, we can in fact generate all strings that have this property, that all binary strings where there are not 2 consecutive zeros, which, is not immediately what you would think looking on this expression. Okay. Next. Okay, all binary string which contains 0, 0, 1 or 1, 0, 0 as a substring. Well, we already saw the regular expression for 0, 0, 1, right? So this one's 0 plus 1 star, right? And then this was 0, 0, 1. And then we had 0 or 1 star, right? This was what we already saw in the previous slide. And now, if we want 1, 0, 0, we can just put it here, right? So generate a binary string, put either 0, 0, 1 or 1, 0, 0 in them, and then concatenate any arbitrary binary string. So this is one solution. And in fact, it's more compact than the solution on the slide. Okay. Bit string with an even number of 1s. So this is a bit more difficult. So the way to think about it is that, well, to begin with, any string with zeros can comply. So we might as well just start a regular expression saying, oh, contain all binary strings which are all zeros. And then the basic idea is that if you want an even number of ones, whenever you have a one, you have to force another one to appear. So let's write an expression that generates all binary strings that have exactly 2 ones in them. And then we can apply the cleanly star to them, right? So a string that have 2 ones in them is just 0 star, 1, 0 star, right? 1, 0 star, right? This is generate all binary strings that have exactly 2 ones in them. And then you can apply the cleanly star to it, right? And we are done, right? And in fact, if you think about it a bit, you can compactify this and get the shorter expression, 1, 0 star, 1, 0 star, cleanly star, right? And you can think a bit why this short expression is equivalent to the original expression. Let's move on. Okay. Bit string with an odd number of ones. Well, we essentially already seen that, right? So again, let's generate a binary string that contains a 1. A single 1, and now we can put in the binary string from above, right, for all even length strings, right? So, you know, string that have even number of ones. So, you know, right? So the basic thing is that you must generate at least 1 string, and then you know, for any other, if you have more than one, you know, you have 3 or 5 and so on, you generate their portion with this string. Now, the way to think about how did they come up with it is that think about your string, right? You have a string, blah 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 blah. There is I ignore the zeros, right? So I have 1 here. I have 1 and so on. And the idea is that I'm chopping them up, right? I chop the string after the first one. I chop the string, and now I go over the 2 ones. I chop it again after the second one, and so on, right? And if I think about it in this way, then we are in a very easy situation, right? Because the substring after the first one can be matched to 0 star 1. Oops, what is that? Don't even. Okay, so this goes to 0 star 1. The second chunk, this one, is going to go to 0 star 1, 0 star 1, star, right? And then what I did put here is that there is, you know, this might be repeating I times, so we put the cleanly star. And then we might have a run of zeros, so we can put a run of zeros here, right? So this is another way to get it, and this is in fact a very convenient way of thinking about regular expressions, right? You have a string, you want it to have some property, you break the string into these chunks, you match every chunk separately by regular expression, and you put everything together. Okay. Okay. And the solution on the slide just uses the answer from the previous slide, which is fine. Bit string that do not contain 0, 1, 1 is a substring. So this is a bit more difficult because regular expression don't really allow you, in the standard way we think about them, to do negation. Although, you know, you can sometimes abuse notation and write it as such, but you're not supposed to do that. So this is a bit more difficult. Okay, so this is pretty tricky. So the first observation is that the string that is all ones is going to be fine, right? So we are allowed to start the string with any runs of ones, right? Okay, now we have the runs of ones, and then we might have a 0, right? But the important thing is that if we have a 0, right, we might have in fact as many zeros as you want, so we put 0 star. This is still a valid string. Okay, and now what happened? Now what happened is that we might have a 1, right? And if we have a 1, and let's think about in fact as this is 1 star 0 plus, right? I want it at least 1 0. And then I have a 1. But if I have a 1 here, the next character is either the final character, either the string ends here, or the next character must be a 0, right? Because otherwise it would contain the string 0, 1, 1, right? So that means that we are allowed an arbitrary long run of 1s in the beginning, right? But then after that, every run of zeros must be of length 1, right? So, so as such, now this becomes much easier, right? So the regular expression is going to be 1 star, and then we can repeat it, right? So 0 plus, right? We allow the run of zeros, then we have a 1, right? And we can do clean star on that. Right? So we're allowed to repeat it every time, but the important thing here is that right, the important thing is that the important thing is that if we're repeating itself, there's going to be immediately a 0 following, right? Now we have to be very careful, right? Because that kind of matches everything we're allowing, except that we might have now a run of zeros in the end of arbitrary length, okay? And that now matches all the string of this type, right? And you have to just verify that it's true, right? So, and the way you verify it is by just using this chunk argument I had before, right? Essentially you say, okay, we have the initial run of 1s, which we can just credit to the 1 star in the beginning of the expression. After that, after every 1 we stop a chunk, right? And those chunks must be of this form 0 star 1, right? So, so that's fine, right? And after this is done, right, we can have a run of zeros, and that's it, right? So this is the answer, and so this is the answer for this question. It's a bit more. It's a bit harder, and you have to think about it, right? I didn't see it immediately. Okay, let's try to do the next one. Okay, odd number of 1s and an odd number of zeros. Okay, so this is pretty complicated. So I would need to think, we need to do it systematically. The observation is that if we have a 0, 0, or 1, 1 in the string, they don't affect the evenness or oddness of the string. So we can just delete them, right, conceptually. So R is just going to be this expression that matches any even run of zeros or 1 or alternatingly. And if we have a string that answers our requirement and there is a portion of it that matches R, we can just remove it from consideration, right? So R is going to be kind of a default fillers, right? Now the important thing is that if I give you a binary string, right, that have the desired property, 1, 1, let's see. Yeah, this is what we want, right? And because the number of zeros, and 1 is odd, then, now I go and I match the fillers, right? These runs of even run of zeros and 1, I delete this, I delete this. Then what I'm left with, and of course I delete this too, right? What I'm left with is just 0, 1, right? Now, if you think about it more generally, what we're going to be left with is a sequence. After we remove the filler, we're going to left with a sequence which is alternating zeros and 1, where the number of zeros and ones is odd, right? But let me know how to do, right? Because, for example, this is 0101 star, right? Star ending with 1, right? This is all the binary strings, I guess, ending with 0, right? Those are all the binary strings that, oops, not quite right. So let's see, what do I want to say? We want, ending with 0, 1, right? So this is all the binary strings that are alternating 0, 1, where the number of zeros and 1 is odd, right? This is when they start with 0, and we can build that the symmetric expression when it starts with 0, right? So this is let's call this expression A, right? So A is all this alternating thing, and now the thing is that we need to use the filler expression, right? Because the filler expression doesn't affect anything. So let's put in the filler expression. The filler expression just, we insert R into A in every possible location, right? So it's going to be R, 0, R0, R1, R0, R1, R star, R0, R1, and the same thing for the other thing, right? Well, R is the expression that they wrote above, right? And again, R, R1, R0, R1, R0, R star, R1, R0, R, right? This is probably way more complicated, where R again is just this expression. Let me write it explicitly. R is the expression 0, 0, or 1, 1 star. Okay, so you put R, you replace in the string above with this, and you get the regular expression for what we wanted. It's a bit more complicated and elegant, but it works. Okay, so let's continue. And they have the solution here. And I think this expression here is follows, I think, from using automatas and so on, which we'll see later on in the course, which is a more systematic way of solving it. This brings us to an important point where with regular languages, since we will have 3 or 4 different ways of representing them, it's important sometimes when you want to define regular language to pick the right representation where writing it down is very easy. In this case, as we will see hopefully shortly, writing it down as an automata is in fact extremely easy. But writing it as a regular expression is pretty painful. And as I demonstrated, it took me a while to figure it out. So it's not easy. Okay. And now, you can define various regular expression identities. This is not one of those things that you have to remember. It's useful to know some of them, but it's like, okay, good to know, right? So concatenating 2 R star expressions equal to R star. A star of a star is a star. R times R star is equal to R star times R, and so on and so forth. Right? Let me not go through those identities. They're not especially interesting. Well, I guess this one tends to be more useful, so let me go through it. So RO plus a star is really equivalent to doing R star, A star, and all of this in a star. And to see why it's true, just observe that in every step when you apply the star here, you are choosing either R or an S, right? So what you're going to have essentially in the sequence, you're going to have a run of R's, a run of S repeating itself. So that's why this is correct. And, And as the slide indicates, there are a lot of other ways to write this down. Okay, so how one prove an identity? Well, you have to do an induction on the length of the expression or something along these lines. It's not something very enjoyable. It's usually very tedious. We might see an example of it, but it's really not, this is not a main, this is not an important thing you need to be able to do. Although, if you can do it, it's good. Okay, that's it for now.